Okay, so thanks everybody for coming. Yeah, so let's just do a quick show of hands. Who did the ROS tutorials?
Recently?
I mean,
Like a year
unless
ago.
you already, who's done the ROS tutorials or is proficient enough with the ROS that they felt they did not need to do the ROS tutorials? It's fine if you didn't, I just need to know kind of like baseline who hasn't. Okay. Did everybody get Ubuntu installed? Did anyone not get Ubuntu installed? Cool, okay. Did everybody understand the ROS tutorials? Did anyone not understand the ROS tutorials? Yeah, okay, good. That's fine. Okay, so the way this is going to work is I'm going to essentially kind of go through the stuff that the ROS tutorials went over, and then we're going to get into actually writing some code that we're going to run on a simulated robot, and then we're going to port that code over directly to a real robot. And ideally, this should kind of give you guys an idea of kind of the whole development process from creating a new workspace all the way to running it on an actual robot. To that end, if you have questions when I'm going through this, or you feel like I'm leaving something out, feel free to just shout it out or raise your hand or whatever you want to do. And that's if you have questions about ROS or anything else, Ubuntu related, Python related, anything you might not understand. Okay, so let's get started. So let's see. I'm starting out in my home directory, so the first thing I'm going to do is make a new workspace. So that's going to be make directory, -P, for making multiple directories. I'm going to call it new workspace, and then I'm going to create a subdirectory called source. Then, now that I've made that, I'm going to change directory to my new workspace. Or rather, I should call it a workspace because right now this is just a folder. And to make it a workspace, I'm going to call the command catkin init workspace, and then enter. That needs to be called again in the source subfolder of whatever workspace you're creating. And that's going to create a link in your operating system so that ROS knows where your workspace is. The next thing I'm going to do is go up a directory, that's change directory ... to go up one directory to my actual workspace, and then I'm going to call catkin make, and that's going to essentially just build everything in my workspace, which right now is nothing, so it's just creating the basic things that a workspace requires. So all of this is pretty much at the beginning of the ROS tutorial. You should have seen this. And mine's taking a while to build because I have a bunch of other stuff in other workspaces that's happening. Okay, so now that I've built my workspace, it's created 2 new folders, build and development, which are going to store stuff related to the workspace. So now that I have my workspace, what I want to do is actually source my workspace so I can use it in this environment. So that's going to be source, and then new workspace, and then development, devel/setup.sh. And that just imports everything related to this workspace into the current terminal window so that I can actually use things and that ROS knows where it is. I can find everything. Now that I've done that, I'm going to actually create a package. So let's go to the source folder, and then that's where we're going to make our new package. So we're going to call our package nav test. Actually, sorry, do not enter that command. I'm going to be using catkin create package, not just making a directory. So we do catkin create package, and then we're going to name it nav test, and then for create package you give it the name, which in this case is nav test, and then you give it any dependencies that it needs to actually run and build your package. So right off the bat, you want to include ROS CPP and ROS Py, which are the 2 APIs that let you use Python and C++ and ROS. For this particular thing, we're also going to be needing 2 other packages. We're going to be needing geometry messages and sensor messages. And then we hit enter, and that creates a new package, which you can see if you list the directory. Nav test is now there. If we move into it, we can then see that it has stuff in it, and that's the bare bones things you need for a package. The CMake lists and package files are essentially what define to ROS what your package is. They tell it what dependencies it has when it's being built. It tells it any executable it needs to generate when you build your workspace, things like that. So, any questions so far? Everything clear? Everybody have a functional package? So then we're going to actually add some code. So the convention, can everybody see that, by the way? Is that?
Try turning off.
Is it hard to see the lights?
A little bit.
Okay, yeah, go ahead and turn off these lights then, I guess.
Is that better?
Yeah.
Okay, so the package we're going to be working on today is a navigation package. And so essentially what we're going to be doing is writing a program where if you have a robot, the robot has a laser scanner. We're going to be taking the laser scanner data and checking to see if there are any objects in the scanner's field of view. If there are, it will find the approximate centroid of the object and then turn until it's away from that object and then move forward until it sees another object and then turn again. It's a very, very simple program. And we're going to do that in Python. So the convention in ROS is that C++ files, compiled files, go in your source folder in your package, and Python files, scripting language files, go in a folder called scripts. So we're going to make a directory called scripts, and then we're going to go into scripts. So we're now in the scripts folder, and so now we need to actually make our file. So let's go ahead and use the command touch, which creates a new file, to create what we call nav node.py. And then we have now created this. We're going to go ahead and make this file executable, which we do by calling sudo mod +x, and that just makes whatever file you then name or files that changes the permissions. In this case, we're adding the executable property to the file.
I think you need sudo there.
I don't think we do either, but I'm doing it. So there you go. Have it. Okay, so now colors change, indicating that this is now executable. This is important if you want to launch files through the ROS launch system rather than having to directly call, Python, whatever. So now we're actually going to edit our file. This can be in the text editor of your choice, just using Vim. So the first thing we need to do is add our, I'm using Vim correctly. We need to add our little executable string at the top that I can never remember, so I'm just gonna go ahead and copy that in here. Okay, so that basically tells the operating system this is a Python file and tells it where it needs to look in order to find something that can run this file. So that's, again, a necessary thing if you be running it through ROS, which we are. The next thing we need to do is import all the stuff we need for this file, which is going to be, first of all, ROS.py, which is the API that allows us to use ROS commands in Python. And then we're also going to need to import the messages we're going to be using for this this file. And so in this case, we're going to be importing two messages. One of them is the laser scan message type, and the other one is the twist message type, which is essentially the message type that lets you send motion commands to robots. Is everybody clear on messages from the ROS tutorials? Is anyone not clear on messages? I assume the silence means everyone knows how messages work.
Not at all clear about something, definitely speak up.
Yeah.
That's the point of this whole thing, is for questions.
I have no idea how messages work.
Okay, thank you. So in ROS, everything works on a message passing topic system. So essentially, you have a set of nodes, and each node is publishing and subscribing to various topics. And so a topic is just a channel of communication between two nodes. So each topic has a defined message type, which is just the agreed upon set of values that can be passed over a particular topic. So, for example, if we want to, there's no topics running right now. So if you have a topic, you can use ROS to examine what message that topic uses, and then further, you can use ROS to examine what types are involved in a particular message. So for example, we're going to be using the laser scan message. So if we want to find out more about the laser scan message, we can do ROS message, and then, is it show? Let's try show.
To show our info.
And then, yeah, I can't remember. And then it's going to be sensor messages slash laser. Okay, and so that is just the package that contains the message definition and then the actual name of the message, which is laser scan, and that shows us everything that this message type contains. And so this is used to store laser scan data. So down at the bottom, it has an array of ranges, which are the actual data points that are output by the laser. It has intensities, which we aren't going to be using, and then it has essentially constants to the laser scanner, which are the minimum angle, maximum angle, step, time step, everything like that. And at the top, it has essentially a sub-message, which is the header, which is a very, very common message type used in ROS, and that gives you the current timestamp when the message was sent, the sequence of messages, so it tells you what number this message is and all the messages that have been sent on this topic, as well as the frame ID, which I'm not going to get into. So this is basically what a message is a just collection of data that you are defining. And so once you have your message type, then one node will be a publisher, which will create this message, set all the data to whatever values, and then publish it on this topic. And then another node will be a subscriber, which will then receive the data and then do whatever operations on it that the subscriber needs to be doing. So that's what messages are. Is that clear to everybody? Anybody have any follow-up questions? Okay. So we're going to be using two messages. Like I said, we're going to be using laser scan and we're going to be using twist. And so we need to import those. And so the way that works is we're going to do I will explain this 1 second. Okay, so that's what importing messages typically looks like. So that sensor messages.message is sensor message.
You might want to say what you are typing, because at least inside of the video, it will be impossible to read it.
Yeah, I'm going to be putting the code online as well, so that should hopefully solve that. So yeah, this is how you import a message from sensor messages.message import laser scan. So sensor messages is the package. .message is because it's in a message subfolder of that package, and then laser scan is the name of the actual message. And then we have a second message that we're going to be importing from geometry messages, which is twist. Okay, so I think that's everything we need here. Oh, yes, that'd be good. Thank you, Alex. Okay, I can actually import it. Okay, so that is all our imports. So now we're actually going to write our node. So the convention that we use in the lab is that in Python, when you're writing a ROS node, you make it a class, because that is by far the nicest way to do it, because everyone knows what classes, almost everyone. I know you don't know what a class is because you're a mechanical person. Does everyone else know what a class is? Okay, everyone knows what a class is. Okay, so for the one person who doesn't know what a class is, a class is an object that holds a collection of member variables and member functions. It's kind of similar to a message, actually. So the nice thing about about putting everything in a class for ROS is that you can have all sorts of disparate functions and variables, and you just have access to all of them. It'll make more sense why we do this probably as we go on. So let's go ahead and define our class. So class nav test, and some of you might be used to Python 3+. ROS runs on Python 2.7, so things are slightly different. One thing is you should pass object as a superclass when you're defining a class in Python 2.7. Don't ask me why, it doesn't matter, just do it. So now we're going to go ahead and define our class. So again, this class, what we need is the ability to take in laser data, find the approximate center of any objects that are within that data, and then use that to turn the robot one way or another. I wish this camera wasn't here so I could go right on the board, but it's there. So in ROS, the way that you drive a robot is, again, via twist messages. And so a twist message is a data type that contains essentially just 6 directions, all 6 possible axes of rotation and linear motion. However, real robots don't usually have all 6 possible axes of rotation and linear motion. Typically, they have 2 axes they can actually move on. They can typically move forward and backward on a linear plane, and they can typically turn in place on the z-axis. So the way that you define motion in ROS is you have a twist message, which again I can actually pull up here because we know how to do that now. So we can do ROS message show geometry messages twist. Yeah, so this is what a twist message looks like. So it has a linear vector, which then contains x, y, and z coordinates, and then an angular vector, which contains x, y, and z coordinates. So for example, if you want your robot to have linear velocity in the x coordinate, you would set linear x to whatever value you want. So real robots, the only 2 axes of motion they have are the linear x coordinate and the angular z coordinate. So anytime you want the robot to move forward or backward, you give it a positive or negative x. Anytime you want to turn left or right, you give it a positive or negative angular z. Does that make sense? Anything not make sense? I have a feeling people aren't asking questions, so I can't be possibly explaining it that well. But let's go on. So that is what we're going to be essentially doing is we're going to find the centroid, and then if it's on the left side of the robot, we're going to say, okay, we want you to turn right until you can no longer see the object, and then go straight. And if it's on the right side, turn left so you can't see the object, and then go straight. So with that in mind, let's actually start writing our class. So the first thing you need in a Python class is an init function, which you can find so. And hopefully this is all pretty standard Python stuff for you guys. If I use any kind of weird Python idiom you guys aren't familiar with, please let me know. I can explain it. I might have just forgotten that I do it. So the first thing we need to do is actually initialize our node. So we're going to call rospy.init node, and then we're going to pass it a string, and this is the name of the node we're creating. In this case, it doesn't really matter. We'll just call it nav node. So then, once we've done that, we also need to tell it whether this node is anonymous or not. And it's going to be false. So anonymity for nodes essentially means that if a node is not anonymous, then ROS is going to be keeping track. It's going to be publishing its true name. So names have to be unique, meaning if you have a node called navnode, and I try to run another instance of navnode, it's going to return an error because there's already one running. In contrast, if we set anonymous to false, then ROS is going to mangle the name that's displayed to the public, which then allows you to have any number of the same type of node running concurrently, which can be good if you want a bunch of the same thing to be happening over and over again, particularly if you have random things. Anywho, so anonymous is by default false, so you don't actually need to include this line, but I'm including it so you guys know it's there. So once we have our node initialized, then we need to actually set up our publishers and subscribers that are going to be using to send data. In this case, we're going to have one of each. So we're going to be publishing twist data to the robot, and we're going to be receiving laser scan data from the robot. So to receive data, we need to use a subscriber. So we're going to call rospy.subscriber, and then requires a couple of parameters you have to pass in. The first you need to pass is the name of the topic it's going to be subscribed to. Typically for a laser scan, this will be called scan. If otherwise, there are other things you can call it, but typically we go with scan. Then you give it the actual message type that you want to use, which is laser scan. And finally, we need to give it a callback function, which we're going to call self.laser callback. Again, I can imagine you guys are not all familiar with callbacks. Who doesn't know callbacks? Who hasn't taken microprocessors or a similar class? Brandon, you know what callbacks are. So essentially, okay, so backing up, who does not know about the concept of an interrupt? Don't be afraid to raise your hand. Okay, it's a couple people. Good. So I'm going to explain it. So when you're running code, typically it will run sequentially, one line at a time until it's done, barring any kinds of, function calls or anything like that. It'll basically run in order. The exception to this is what are called interrupts. And so an interrupt is a flag that's set by the processor when a certain event happens. And when that happens, that tells your code that it needs to stop what it's normally doing and go do what's called an interrupt service request and handle everything related to the interrupt and then go back to its normal execution. So a common example in embedded systems is you might have a timer that the processor is running, and every 2 seconds you want a light to turn on and off. So you'll set the interrupt to be active, and the processor will time 2 seconds and then throw a flag. Your code will stop running, go into this interrupt. The interrupt will turn the LED off or on, and then go back to your original code. And so the thing about interrupts is that they are not part of normal operation of code. And what that means is they can be dangerous because, if you have your code doing one thing and you have this interrupt that's supposed to fire periodically, most of the time you can treat it like they're running at the same time. However, if your interrupt does a lot of stuff, if you're in your interrupt for more, macro time for more than like milliseconds, then everything else is not actually running, and so it's all going to slow down and your code is going to stop working. This is particularly dangerous if you start a whole new thing in your interrupt. If you start basically running a whole new process, that's a very bad thing to do because the interrupt never actually leaves. And then if there are more interrupts, those aren't actually going to run either. So that's what an interrupt is. I hope that made sense. And so the reason that's important is that ROS and other message passing systems have what are called callbacks. And so a callback is kind of a specific type of interrupt, or rather, it's a function that handles a type of interrupt. So the way it relates to ROS is that when a topic has a message published to it, everything that's subscribed to that topic receives that message. Then the node that is subscribed to that topic has to have a way to handle the message, and so that's what a callback is. It's an interrupt essentially that is called whenever a new message is received, and the callback then runs and then exits. And so in this case, the callback we have created is called laser scanner _ callback, and so it will run every time the scan topic receives a new scan. And so we will define in just a second what that's actually going to do, but first let's finish the rest of our initializer. The next thing we need is a way to actually publish data. And so we're going to create a publisher object, which is going to be, we'll call it self.velocity publisher. And that will be rospy.publisher. And then we again give it the topic that's to be publishing to, which in this case is going to be a very long string. Don't ask me yet why this is a thing. So this is the name of the velocity topic we're going to be publishing to. Typically, the convention is you call it command velocity, CMD_VEL. That's the general accepted format for robots. We are going to be running today on the TurtleBot, which is on the floor there. And so it does not use the standard convention of command velocity. It has a bunch of fancy intermediary steps, so we're publishing to this topic. The next thing we need to do is, again, give it the message type, which is twist, and we don't have to give it a callback because we're initializing an object that we will then use to publish messages. We do have to give it a queue size, which I don't remember what that actually is. Queue size, okay. We have to give it a queue size parameter, which we're going to set to 10. So that's the number of messages that it can have essentially bottled up before it stops just trying to send things, or for dropping packets. So it's actually a new thing in ROS Indigo that's necessary. I'm running ROS Hydro where it is optional, but I think a lot of you are probably running Indigo, so that is not necessary, but they will throw a warning. So they're in the process of making that mandatory for people. Yes.
I really can't read the red text of the strings. Could you change that real quick?
I can't because it's in Vim.
You
I
can't?
can
Oh.
switch text editors though.
Okay.
It's, that will.
It's not showing up on here either.
I'm gonna put the code online, so that's more to
Give
see
us-
me and
okay.
hear me rather than actually,
Reading code.
yeah.
Okay.
That did not copy successfully. You copy stuff and then
You
again.
get to right click.
You can't right click.
I
It's
think it's
always
not
Y.
right.
That's right.
What's
Ah.
What's the Y?
Okay.
It
I'm
might
gonna-
be easier to read with a white background.
What? Okay.
Sorry.
Who else is having trouble reading this? Everybody. Okay. Would it be easier on a white background?
Yeah, probably.
Okay. Well.
It's
That's
less
fine.
reflection from the lights with the white
Can
background.
this be? Is this readable?
That's much better than
Yeah.
the other one.
Okay. So let's just go with this then.
But I would zoom in a little bit.
Okay.
Yeah.
Better?
Yeah.
Okay, so we're gonna continue on from here. So now we have those things don't come in here yet. I haven't talked about them yet. Okay, so now we have our initializer for. Is that everything I have in there? Yeah. Okay.
Then subscriber yet.
Okay. We did subscriber already.
Oh,
We'll just call back.
different order.
So now we have our initializer, and that's basically all we're going to put in there for now. And now what we're going to do is define our callback function. So our callback function is going to be where we handle the data we get from the laser scanner. And so as I was saying before, you don't want to do too much stuff in callbacks. A lot of the time, all a callback needs to do is save the data somewhere, set a flag that there's new data available, and then end. We're going to do a bit more than that in this callback, but again, you don't want to do everything in callback. So let's go ahead and start writing it. So it's going to be called laser callback, and we're inside a class, so it has to have the self-referential parameter first, and then it also needs a secondary parameter that is going to be the data that is being passed by the topic. I'm calling it data, you can call it message, the name is arbitrary. So now we actually have to do something with our data. So as I said before, what we're going to be doing is looking through the data to find if there's an object, first of all, and if there is an object, we're going to take the centroid of that object and then throw that back out. So the first thing we actually need to do is add a few instance parameters to our class. So we're going to want an object variable, and that'll be set to tell us whether there's an object in our field of view or not. And then we're also going to want a centroid parameter, which will tell us the angle of the centroid of the object. So where 0 is the front of the robot, and then negative is off to the left, positive is off to the right. And this is going to be in radians, by the way. So I think that's the two things we need. Yep, so that's what we're going to need for our callback. So then, for actually, yes?
Is there, I know with C++ they have sort of a comment command, is it like where you can just like leave a message for yourself or other users? Does this have that as well?
It's a hashtag.
Yeah. Yeah. So yeah, okay, so comments in Python are going to be the pound key, and then you type whatever. It's a single line comment. You can also add bigger comments by using triple quotes. So that's quadruple quotes.
Quadruple quotes.
So then that lets you have as many arbitrary lines of stuff as you want, and that also functions as a comment. Okay. Any other questions before I keep going? Okay, so let's find the centroid of our laser data. So as we saw, let me pull up that scan again. So we have a couple things in the scan message that we can use, and we want to actually get a bit more here. Okay, and so we're going to use the parameters of the laser scan message type to make our function as generic as possible. And so the first thing we need to do in order to find the centroid is we need to go through each scan, each data point, where the data points start at the minimum scan angle and then increment by the angle increment until they get all the way up to the max angle. And so at each of those points we'll have a range value which will be from 0 to the range max value. And so that will, and so what we're going to do is at each point, if it is below a certain threshold, meaning it's returning a close enough value that there's probably something there, we're going to take its angle and we're going to add it to a centroid value. And then to the next one, if it's below, we're going to add it to the centroid value. We're going to go through the whole thing, and then once we're done, we're going to take the number of values we saved and then divide by that, and that will give us the average angle amongst all of the data points we saved, and that'll tell us approximately where the centroid is. Does that make sense? Does that not make sense to anybody? Okay. So let's go ahead and get started. So we're going to have a temporary variable just called centroid, which is, so it's not a class or not an instance variable, it's just a local variable. And so we're also going to have an angle variable, which will start at, that's correct, yeah. So in Python, in ROS specific Python, when you have a message, it is an object. So you can access its members like you would a normal object. So in this case, I want to know the minimum angle for this laser scan, so I'm just doing data, which is the message dot angle min, because like you can see it right here, and that'll return that value for me. So I'm going to assign that to angle, and the angle is going to be the variable we're going to use to increment through the data angles until we get all the way around. So now we're going to go ahead and increment through that data. So we're going to say for point in data dot ranges. And so with this, we're going to increment across all of the data points in the ranges array, and then point will be representing the actual value at that location. Following so far? Okay. So what we need to do at each point is, first of all, check whether or not the data point is lower than our acceptable value, meaning there is probably an object there. So to do that, we're going to say if point is less than, and then we define what the minimum acceptable value is. I'm going to say it will be data dot, I believe it's range min. So I'm going to say that if a particular value is less than 1/9 of the maximum range, it's considered to be an object. And the reason why it's, but
you're using the range min variable.
oh, thank you, Billy. That should be range max. That would be useless. So now it's actually going to be, if it's less than 1/9 of our total distance we can measure, then there's something there. So, and I don't know how familiar you guys are with Python 2.7. I don't know if I don't know what's used in programming classes these days, but unlike 3+, there is no automatic conversion from floating point to integer and vice versa. So if I were to say do this, and if this were an integer and that's an integer, the resulting division is going to be rounded off at the at the point. So if you want to make sure your division is floating point division, you want your constants to be floating point, so 9.0, or just 9 point, like 9.0. Random side note. So now, if our point is part of an object, then we need to update our centroid. So we're going to do centroid. We're going to increment it by our, oh, that's not the right thing, by our angle. And yeah. Then after that, we're going to say, what are we going to say next? Oh, right, I forgot something. Bear with me, people. We also need a count variable, which will tell us the number of points that we're actually adding to our centroid value. So then we need to also increment our count by 1. Now that we've done that, we are done with that. Okay, so basically we're going to go through and then check if the point is in our object. If it is, update the centroid. And then after we've done that, we need to increment our angle counter so that our angle matches with the next data point. So to do that, we're going to do angle plus equal, and then we're going to add data dot angle increment. Double check. Yes. Okay. That's just going to add whatever the step size is between each reading, and yeah. So the result of what we've done so far is it will go through all the data points and check each angle now. Does this make sense to everyone? Does not make sense to anyone. Okay. So now that we have that, what's the next thing we have to do? Right, okay, so then we need to actually take these values and convert them into an actual usable centroid. So the way we're going to do that is we're going to say self.centroid, which is the actual instance variable, which we're going to be looking at later, and we're going to assign it to centroid, which you might remember is the sum of all the angles that are in our object, and then we're going to divide that by the count, which is the number of actual hits we've gotten, and we right, okay. And we do one other thing. First of all, we're going to make sure centroid is a floating point number because of that floating point division that I talked about earlier. And then we're also going to have to make sure that count isn't 0, because if count is 0, which is entirely likely and expected if there's no objects there, then it's going to return a divide by 0 error. So we're going to do so that might look real weird to some people if they haven't seen that before, but that is, has everyone seen conditional assignment in C? Has anyone not seen conditional assignment in C?
Conditional what?
I'm sure someone has not seen conditional assignment in C. Okay, so in any language, conditional assignment is just a method where you can say, you know, this variable equals one thing if one condition is true and another thing if another condition is true. So in Python, it looks like this. You give your initial assignment and you say if whatever thing is true. So in this case, if count is greater than 0, we're going to assign it to this. And then we're saying else 0. So if it's not greater than 0, we're just going to make the centroid 0. Does everyone understand conditional assignment now? Yes. Okay. Hopefully. So now we've actually gotten our centroid object, or our centroid value, and we're saving that there. And then the next thing we need to do is set our flag as to whether or not there is an object present at all. And so we probably don't want to just say if there's any count, because there's always a chance of a few stray measurements triggering that there's an object there and there's nothing there. So instead, we probably want to say if there is a certain percentage of the total number of scans that say there's an object, then we'll say, okay, there is probably an object there. So we're going to do self.object gonna do this. We're doing another conditional assignment, people. So we're gonna say it's true if the count. I can't remember how to do this actually. All right, okay. So bear with me. I'll explain this in a second. Right, okay. So what I'm saying here is essentially we're taking count divided by the number of data points we have, which is that count divided by length of data.ranges. So that essentially gives us a proportion of the number of hits we got to the total number of data points. And then we're saying if that is greater than 2%, there's an object there. If it's not, there's not an object there, so we assign it to false. Following so far? Yes, no. Okay. So that is that. So that should be now everything we actually need for our callback function. So, and that's a reasonable amount of things to do in a callback. We're not doing any kind of major things that will take a lot of time. We're just doing some simple arithmetic, and then we're saving some things out, and then we're done. So now that we have our callback, and we're getting, so basically every time there's a new laser scan, which will be about every 10th of a second, depending on your laser scanner, we're going to be updating our centroid, updating whether or not there's an object present at all, and then jumping back out. So the next thing we need is a way to actually deal with this information that we now have. And so we're going to be doing that with essentially what you could call our main function, which we're going to call run. And we'll accept yes.
Could you move it over to the right a bit? I didn't get that last one.
Yes.
Thank you. Okay.
Okay. So we're going to be creating a function called run, and that's going to basically be a loop that will drive our robot for us. And so within our run function, again, we're going to have a loop, and inside that loop, we're going to check if there's an object present. If there's an object present, we're going to turn away from it until there's not one. And if there's not an object present, we're just going to drive straight. And so the first thing about, there's two things about loops in ROS you should know. One, you never want to have a loop that just runs as fast as it can, because that can be bad. First of all, because usually it's going to run faster than it needs to, and you're going to be using up a bunch of clock cycles when there's going to be other nodes that could probably use them better. Two, a lot of robots can't, in fact, all robots and most topics can't accept faster than a certain rate, and if you try to publish faster than what they will accept, it just doesn't do anything. So you want to always limit the speed of your loops, especially if they're publishing things. And even if they're not, you still want to do it usually. I'm not up here because I'm too cool. So the way we're going to do that is excuse me, is what give me a second, is with what we call a rate object. And so rate is a feature of the ROS time library, which is part of ROS Pi. And what it does is it tries its best to maintain a certain rate of execution on your loops. And so the way we do this is we say, we'll call it this RT equals ROS Pi dot rate, capital R, and then we give it the rate, and that's in hertz. So if I give it 10, it will execute 10 times every second. And 10 is a pretty good number for something like this. I usually work in multiples of 10. So once we have a rate thing, then we're going to define our actual while loop. So we're going to say while. And here's the second part of loops in ROS. You never say while true, even if you're going to be running forever, because if you do while true, that's fine. If you're running it by calling Python and then your file name, you press Control-C, or close out the thing, it'll stop. But if you're running it through ROS launch system, Control-C doesn't work anymore, as it turns out, if you use true. So what you use instead is ROSPy dot, rather not ROSPy dot is underscore shutdown, open and close. And what that does is that's just a call that tells you is ROS shutting down? And so 99% of the time it's going to return true because it's not shutting down. But when it is shutting down, for example, when you press Control-C on your ROS launch terminal, then it'll say false, and then it'll stop, and then your program will exit just like normal. So that's, you always put that in your while loops. Anything that's going to run for more than like a millisecond needs to have this in it, because you don't want your program to be stalling while you're waiting for it to shut down. So that's, we're gonna have that there. We'll go back to what's actually gonna be in our while loop. But after our while, at the end of our while loop, after we've done everything else, we're gonna then call rt.sleep. And with that, so what that's doing is that's going back to our rate object earlier. Once everything's happened in our while loop is done, rt.sleep is going to check the amount of time that's passed since our loop executed, and it's going to then sleep for an amount of time that is appropriate to maintain our 10 hertz execution. So again, you always want to make sure that's there, because otherwise things will crash and burn and things will not work. So now we can actually write our while loop. So what we're going to do in our while loop again is first we're going to check whether there is an object or not. So we'll say if self.object. So if there's an object present, then what we need to do now is turn away from the object. So what we're going to do is we'll say if self.centroid is less than 0, so meaning it's now on the left side, that means we want to turn to the right. And that means we need to send the robot a velocity command turning to the right. And so the first thing we need to do at the top of our while loop is create a twist message that we're going to modify. So we will say velocity message equals twist, and that just creates an empty twist message. Everything is now set to 0. You could publish this and it would just stop your robot. It's a valid message. So now, again, centroid is to the left, so we want to turn to the right. So we're going to say velocity message dot angular, because we're turning, dot z, because we're turning on the z axis, because it's the one up front, it's the only angular axis we have, and we will set our angular velocity to a positive value, because we're turning to the right. And so we're going to set that to 1.0. So then the next thing we're going to do is just, if it's not on that side, it's either the 0 or it's on the right side. So we're going to then say go in the other direction. So we will say velocity message angular z equals -1.0.